In this video, I'm going to go over gears, pulley drives, and sprockets. All right, so these three powertrain elements transfer energy through rotary motion, change the speed of the rotation, they change the direction of the rotation, and they change the amount of torque available to do work. All right, so let's look at the parts of the gear. All right, so these gears are known as spur gears. The circle marked in red shows the outer limit of the teeth. The green circles are known as the pitch circles. The pitch circle of a gear is very important as it is used by engineers to determine the shape of the teeth and the ratio between gears. The pitch of a gear is the distance between any point on one tooth and the same point on the next tooth. The root is the bottom of the gear wheel. The pitch point is the point where gear teeth actually make contact with each other as they rotate. All right, so when we refer to gears, we look at torque instead of work because they rotate in a circular motion. All right, the symbol for torque is the Greek letter case ta. All right, so torque is a measure of how much of force acting on an object causes that object to rotate. Whenever you have a rotation, you're going to basically have a torque. The object rotates about an axis, which we will call the pivot point. The distance from the pivot point to the point where the force acts, or the pitch point, like you saw on the slide before, is called the moment arm and is denoted by an R. So torque, again the Greek letter ta, is equal to the radius times the force. Right? So torque N equals radius N times force N, or also it can be written as torque out would be radius out times force out. We know that force in has to equal force out. So the torque in divided by the radius in would equal torque out over radius out. I've just rearranged these equations here to set force by itself. So then the gear ratio is the radius out divided by the radius in, or also can be looked at as torque out over torque in when we're trying to find those gear ratios. Okay, so gears can be found in many machines in a workshop or factory, and at home they are often an important part of mechanical devices. In a car, the gears help the driver to increase and decrease speed as he or she changes the gears with the gear stick. The gears opposite are called spur gears because they mesh together. As shown in the figure, gear A is called the driver because it's turned by a motor. As gear A turns, it meshes with gear B and it begins to turn as well. So gear B is called the driven gear. When finding the gear ratio, we can also look at the number of teeth, right? Just like here with it radius out over radius in and torque out over torque in. We can also find the gear ratio by looking at the number of teeth. It would be number of teeth out divided by number of teeth in. So my driven gear here, which is out, is 75 teeth divided by 25 teeth, right? My in gear. And that's equal to 3-to-1 ratio, or just 3 is fine to represent it that way. So gear A has 25 teeth and gear B has 75 teeth. If gear A turns 1 revolution, how many times will gear B turn? Right, so this one goes 1 time around. Gear B then is only going to end up going 1/3 of the way around. So gear A must turn around 3 times for gear B to rotate once. That's where we get the gear ratio then would equal 3. Right, so the gear ratio is equal to the number of turns of the effort gear, driver, necessary to turn the resistance gear, or the driven, 1 time. Right, so which gear revolves the fastest then? Right, if you think if gear A has to turn 3 times when gear B only turns once, then gear A would have to be moving faster. Because when we look at angular velocity, we're looking at number of revolutions divided by time. All right, so let's look at this in a motorcycle wheel turns 3,600 times while being ridden for 6.40 minutes. What is the angular speed of in revolutions per minute? So this letter here is the Greek letter for omega, just so you know. And then so we say number of revolutions, 3,600 revolutions divided by 6.40 minutes is 564 RPMs, which is revolutions per minute. All right, so whenever you see RPM, that's what it stands for. Okay, so how does angular velocity and torque relate? All right, so the power transfer in a rotary device is given by power transfer equals angular velocity times torque. So again, we're going to set it up as power in would be angular velocity in times torque in, and power out would be angular velocity out times torque out. So we know that power in has to equal power out. Set these up equal to each other then. When I rearrange that, notice that our equation, the torque out divided by torque in, that the angular velocity is opposite because angular velocity and torque are inversely proportionate. So when we speed up a gear, all right, we increase the angular velocity, it means our torque is going to go down. So if we're looking for more torque, we need the the output gear to be going slower. We need the angular velocity to be less if we're trying to increase the torque. And we can do that by changing those gear ratios, by changing the number of teeth in them. Okay. So here, first let's talk about what each letter means. The variables that you need to know is N is the number of teeth, D is the diameter. Sometimes you'll see an R for radius. Either one works. Right? The omega sign is the angular velocity, and the tau sign is torque. Whenever we look at these, here we're going right to left. The in gear is on the right, the out is on the left. So then we get all of the information that is written on here and put it into its correct places for in and out. All right, so here's the equations that we just talked about. Number of teeth out over number of teeth in, diameter out over diameter in, and we can set all of these equal to each other. So if in a problem I have number of teeth and I have maybe torque out and I'm trying to find out what the torque in would be, or again I have the number of teeth and I know how much torque I put in, I can get torque out by putting them equal to each other because all of these equal the gear ratio. So this particular problem here, where the one on the right is in and the one on the left is out, we can set up our gear ratio. All of these are equal to each other, and as you can tell, they're all equal to 2. We do not have a unit on gear ratio, just like we didn't have it on mechanical advantage, because each of these are going to cancel out. All right, so far you have read about driver gears and driven gears. An idle gear is another important gear. In the example, gear A turns in a counterclockwise direction, and also gear C turns in a counterclockwise direction. The idle gear is used so the rotation of the two important gears is the same. The example below is a gear train. Next, we will examine how to find the gear ratio for a gear train that has more than 2 gears. When the number of shafts in a gear train is odd, the first gear and the last gear are going to rotate in the same direction. When the number of shafts is even, the gears rotate in an opposite direction. Just a little FYI information for you to know. Okay, so let's kind of talk about whenever we have a longer gear train. Right? We're going to look at these as kind of like compound machines, right? Because we have one gear to the next. So my torque out would equal my gear ratio times torque in, just like force out was equal to mechanical advantage times force in. In this, though, we need to see that our gear ratio total is each ratio multiplied together, and we're going to use that in the next in the next slide. So here I have a longer gear train. All right, I have A to B, and then B to C, and C to D. Okay, so we're still gear ratio. We only have the number of teeth, so we're going to use that. Number of teeth over number of teeth out divided by number of teeth in. Okay. All right, so gear A driving B is going to be out over in. So we have 12 divided by 20. Okay, then we have B to C, just like we talked about in the one before. We're going to multiply these together. So B to C is 5 divided by 12, because now 5 is our out and 12 is our in, right, times the next one, which is C to D. So we have D is our out, 5 is our in, okay, which equals a 1-to-1. And notice that every single time the gears B here, or A, okay, let's look at this. B is the one on top. Again, B is on bottom. It's always going to cancel out. C here is on top, and it's on bottom again. It's always going to cancel out. So really, all we have to do whenever we have a longer gear train is look at the gear ratio of the first one and the last one, because the others will always cancel out. Right? So if gear A and D were directly connected to each other, the result is going to be the same. All right, so what would the gear ratio be if the last gear was 40? Like I said, B and C we can ignore because each time they cancel out. So we would just have 40 over 20, which is a gear ratio of 2. So compound gear train. Compound gears are used in engines, workshop machines, and in many other mechanical devices. In the diagram, gear A is actually 2 gears attached to each other, and they rotate around the same center, so the blue and green gears rotate at the same angular velocity. Sometimes compound gears are used so that the final gear in a gear train rotates at the correct speed. All right, so let's talk a little bit more about that. In this compound gear train, notice the dark purple gear is going to turn twice the rate of the blue one. Even though these are the same size, they are going to rotate at different speeds because it is meshed with the smaller one. They're sharing a shaft. So this one is going to turn faster, making the one on bottom turn faster. And if it was twice the size, we're looking at twice as fast. All right, so going a little bit farther, the purple gear turns twice the rate of the blue gear. The green gear turns at twice the rate of the purple gear. And the red gear turns at twice the rate of the green gear. All right, so this is how we can speed up our the last gear. That's how we can speed it up, is by using these compound gear trains. If we're wanting to increase our torque, though, we would not want to increase the speed. Instead, we would maybe use a smaller one going to a bigger one to try to decrease the speed if we're wanting to increase our torque. Okay, again, if we're still trying to speed it up, notice the large gear is 5 times the size of the smaller gear. Right, the purple gear is driven at 100 RPMs. The gear ratio to green gear is 1-to-5. Okay, so the angular velocity for the green gear is 500 RPMs. The green gear is driven at 500 RPMs now. So the gear ratio to the red gear is 1/5. So our angular velocity for our red gear is 2,500 RPMs. So it's going to speed it up by a huge amount. Again, the faster it goes, though, my torque is going to be less. But the middle, on this example, the 2 middle gears share a common axle, so they rotate at the same speed. This allows the final gear to rotate slower and produce more torque than if it were connected only to the driver gear. Again, notice how we're going from a large gear to a smaller one, and a large to small. All right, so this says it allows the final gear to rotate slower. I keep doing that. For some reason, these examples like to go from right to left. So we're saying that the green one is our driver gear. It's going from a small one to a larger one. And that's why it's going so much slower, and it's going to then increase our torque. Okay, so we're going to examine this a little more. What is the gear ratio? Right, well, I need a gear ratio from A to B, and I need a gear ratio from C to D. Like the compound machines, I need to then multiply those two together to get my final gear ratio. Again, in out over in in. All Right? So my out is 40, my in is 10, so it's a gear ratio of 4 for A to B. Then I need my C to D. It goes from 20 to 50, so 50 divided by 20 is 2.5. Now I need to multiply those two together. So 2.5 times 4 equals 10. So my total gear ratio for this compound gear is 10. Okay, so drawing gears. It would be very difficult to draw gears if you had to draw all the teeth every time you wanted to design a gear system. For this reason, a gear can be represented by drawing two circles. You'll see me use that in some of the problems. Mine might not be perfect circles, but I get that done. A pulley system are used when there is a need to transmit rotary motion. The diagram below shows a simple system comprised of two pulley wheels and a belt. It is a simple mechanical device to winch up and down a rope. When the motor is turned on, it revolves the driver pulley wheel. The belt causes the driven pulley wheel to rotate as well, winding out the rope. Right, so pulley wheels are grooved so that the belt cannot slip off. Also, the belt is pulled tight between the two pulley wheels in tension. The friction caused by this means that when the driver rotates, the driven follows. We're looking at the same equations. Right? This diameter out over diameter in equals angular velocity in over angular velocity out, which equals torque out over torque in. Of course, we don't have teeth on this one, so we're not going to see number of teeth. But it's worked the exact same way. Okay, all of these equaling the gear ratio or pulley and belt system ratio would be 3. Right, sprocket and chain system. Everyone has seen a bicycle or used one and noticed that it is driven by a large driver gear wheel that pedals attached. Smaller gears at the back are given round. Smaller gears at the back are driven round, in turn driving round the back wheel. As the back wheel turns, the bicycle moves forward. Gears driven by the chains are used in machinery, motorcycles, car engines, and many more applications. And so a chain is made up of a series of links that the links held together with steel pins. This makes a chain a strong, long-lasting way of transmitting rotary motion from one gear wheel to another. Chain drive has one main advantage over a traditional gear train. Only 2 gear wheels and a chain are needed to transmit rotary motion over a distance. With a traditional gear train, many gears must be arranged, meshing with each other in order to transmit motion. Okay, again, equations are the same as the gear. We have the number of teeth on this one as well because we have teeth on the sprocket and chain system. All right, so again, our ratio is 2. All right, so let's compare them a little bit. A pulley has a belt, a sprocket has a chain. Right, the advantages of a pulley is it's quiet, no lubrication needed, it's inexpensive. A sprocket has no slip, it's a greater strength. It also is going to have a better torque because it gets into the chains and it's going to have a better torque than the pulley. The disadvantages, the pulley can slip. The sprockets cost a little bit more, they need lubrication, and they are noisy. Okay, I'm going to work problems in the problem videos, which you can watch next.